All right. I wanted to remind everyone as you're joining to please mute your microphones and turn off your cameras unless you are the presenter for our talks here today. My name is Wendy Crone. I'm the Karen Thompson Meddy Professor of the Department of Engineering Physics at the University of Wisconsin-Madison, and it's a pleasure to welcome you on behalf of the Organizing Committee for the Frontiers in Mechanical Engineering and Sciences webinar series. You can see the members of our organizing committee here, and we have Devesh Ranjan to thank for pulling us together and creating this wonderful seminar series that we're enjoying here during a time when we're not able to interact in person. I wanted to give a very brief mention of next week's talks. They will be on October 9th at the same time. The theme is data-driven modeling. Our moderator will be Professor Kurt Bronkhorst from the University of Wisconsin-Madison, and we'll have two speakers, Mark Fuge and Khalid Jawed, who are both assistant professors, and they will be presenting in this format next week. Today, our theme is mechanics of materials, and I will be giving a very brief introduction to our moderator, J.N. Reddy. He is the O'Donnell Foundation Chair Professor, University Distinguished Professor, and Regents Professor of Texas A&M University. He's a member of the National Academy of Engineering and is known worldwide for significant contributions to the field of applied mechanics through his pioneering works on the development of shear deformation theories. He's also an author of widely used textbooks. His contributions to the field are extensive, and his bio in the advertisement summarizes some of his accomplishments. Let me hand over the session to our moderator, J.N. Reddy.
Thank you, Wendy. I welcome all of you to this symposium. And I was looking at the title, Mechanical Engineering and Sciences, but I would have probably preferred to call Mechanical Engineering Sciences. So what I'm getting at is this is the mechanics day today, two talks, and I really characterize mechanics as a branch of engineering physics that to as the objective of seeking fundamental truth under the sun. It can be fluid mechanics, heat transfer, biological engineering, geological, name it. So it's a really broad area, although some reason in last decade or so, many universities removed the mechanics name from the departments, but mechanics is really thriving in the background because it's the fundamental engineering science. So especially my comments should be taken in the spirit of conducting basic research in whatever we do, passion, and young folks who are logged in. I like you to understand that involving in whatever you do for a long length of time is what leads you to new discoveries and findings, not just move on from one to the other in the interest of only accumulating number of papers. That I think is not as consequential as making a deep contribution in a topic area of your choice. So with those comments, I will introduce the speakers. I think we are switching, if I understand correctly. So Professor Maran is from University of Wisconsin at Madison, and his research focuses on advancing fundamental knowledge of process, structure, property, function relationships in structured materials such as hierarchical carbon nanotube foams and mats, gradient nano-grained metals, polymer nanocomposites, and non-Hermitian and parity time symmetric metamaterials. So he has earned a doctorate and also Master of Science in Mechanical Engineering from Caltech. And then he did, of course, he got his bachelor's degree in civil engineering from University of Peradeniya, Sri Lanka. Uh, Before joining Wisconsin, he was a postdoctoral fellow in the Department of Material Science and Nanoengineering at Rice University in Houston. Today, he's going to present, I think, let me introduce the second speaker before I give the stage to you, okay? Second speaker is Julianna Abel. And I don't know if you are anyway connected to John Abel or not, but she is the Benjamin Mayhew Assistant Professor of Mechanical Engineering at the University of Minneapolis and I guess Twin Cities. And Juliana works in a very interesting area, somewhat closely related to my own interest. Our interests are in the model-based design of smart materials and structures with an emphasis on geometric and textile-based architectures for creation of novel actuators, sensors, and energy harvesters. Her research establishes frameworks to design and synthesize smart material technologies to enable new aerospace structures, medical devices, and consumer products. And I think we as a group are eager to listen to both of these young people. So we'll start with Thevamaran. So now you can take it and go.
So let me share my screen. Okay, can you hear me? Can someone confirm that you can see my screen and hear me clearly?
Looks good.
Okay, perfect. Thanks, Jian, for the nice introduction. It's a pleasure to be here in this unusual time, at least present online, and give this talk. So my sincere thanks to the organizing committee for putting together such a wonderful platform for young researchers to share what we are doing. And also thanks for those who have nominated me for this particular talk. So my name is Ramathasan Thevamaran. You can shortly call me Deva. I'm an assistant professor at the Department of Engineering Physics of University of Wisconsin-Madison. I have been here for about 3 years now, and thanks a lot. All my thanks goes to my students, collaborators, and colleagues for taking me on a very enjoyable journey over here. So I'm looking forward to sharing part of the journey on microballistics, okay? So the brief outline for this talk is, first I'll introduce what we do in our lab in a broader sense, and then get into today's topic. One is on piezoelectric polymer, and other one is on gradient nanograin metals. These are two applications of this microballistic technique that I will discuss. The motivation for our research in our lab comes from certain extreme events we encounter in our life. It could be the sport-related collisions you see over here, where you need to protect humans from these head injuries, right? So these repeated concussion can lead to traumatic brain injury. So it is important that we develop gears that can help protect them. Not just about humans, also we need to protect our engineering systems. It could be as simple as your iPhone falling down and cracking. Nobody likes that. Or else it could be like the spacecraft that are seeing increasing threat from space debris and micrometeorites. When you look at these events, one thing you can immediately see is the impact velocities vary drastically from 1 to 10 meter per second in these small impacts versus like several kilometer per second impacts in the space, right? So they correspond to very different strain rates in different types of materials. So one thing that is common that you can see in all these conditions is that materials are pushed to the extreme. So we need to design materials that can perform in these extreme conditions. So when you think about that, structured materials provide us a very unique opportunity. What these structured materials are is that we can deliberately structure the material in different length scales, going from nanometers all the way up to macroscale to achieve certain bulk properties. So with this perspective, in our laboratory, we aim to develop fundamental understanding of the process, structure, property, function relations in structured materials, and then we try to create innovative structured materials with superior specific properties. Specific properties mean properties per kilogram of material, so that we can go towards lightweighting and resource efficiency. And then with these materials, we try to create novel functionalities as well. There are three classes of materials that we focus on. The first one I call hierarchical materials. These materials, for example, you see a carbon nanotube form. That is a macroscale form, but if you zoom in mesoscale, you have these vertically aligned bundles, and if you zoom in further to microscale, you can see this entangled forest-like morphology, and you look at one single nanotube, that's a multi-volt carbon nanotube in the nanometer scale. So across these length scale from nanometers to macroscale, you can tune these structural features to affect the bulk properties. That's what we do in our lab, and the outcome of that is, for example, you can see in this video, if you take this material and shoot it against a target attaching to a striker, you see that it goes and deforms again the target in an orderly fashion, and it completely recovers back. During this process, it absorbs a lot of energy in the order of more than 200 times times the energy absorption by any commercial forms of similar density. Another kind of material system we focus on is called the non-Hermitian metamaterials, where these materials don't have apparent geometric symmetry, but they do have symmetries in the dynamic equations of motion. For example, this parity and time reversal symmetry. When these symmetries are broken, they can lead to these kind of unique bifurcations called exceptional points. Around these points, you can have extreme wave matter interaction that we can utilize to create hypersensitive sensors and directional wave transport. The third class of system we study is the nanostructured material, which I will focus on the topic today, in the talk today. So the first part, I will talk about the piezoelectric polymer films. So the concept of armor is an evolving concept. It depends on the threat we face in the current time. So always this evolution of armors have been accompanied by the development of novel advanced materials. I'm hearing some feedback. Okay, thank you. Yeah. So when you think about these armors, there are two things you would like to have. One is high specific penetration energy, so that you can absorb the energy of the projectile. Second thing is that you want to rapidly delocalize the concentrated stresses from the projectile such that you can avoid localized failures. In the nanomaterials regime, one of the very first studies that had been done with this microballistic system was on graphenes. So these graphene, multi-layer graphene have been shot by microprojectiles. It has been shown that these graphene turns out to have high superior penetration energy compared to other bulk protective material as far as this Kevlar or PMMA, aluminum, steel, and also some other nanomaterials. This was the first promising thing that launched us towards this nanomaterial regime. And of course, we have now developed much better materials that I will show you shortly. So what this microballistic testing system is that you do the ballistic testing in a miniaturized scale, where your projectile is a microprojectile. And then what you're doing is you have a target material deposited on a transmission electron microscope grid, and then you're launching these microprojectiles selectively, one particle at a time, using lasers. How you do that is you create a propulsion mechanism where on a microscope glass slide, you have a thin layer of gold that absorbs this laser energy and become gold vapor. And that is trapped between the PDMS rubber and the glass, such that this rubber expands and launches the projectile. So this entire action happens in this microscope, as you can see over here. While doing this, we have transverse imaging at ultra high rates, down to like every 12.5 nanosecond we can image with our system. And we vary the projectile velocities from 100 meters per second to 1 kilometer per second. So this gives a really good opportunity to study small scale materials in very high strain rate regimes. So if I show this is how a PDMS bubble expands to launch the projectile, and here you see a projectile penetrating a target, and post-impact you can take the target and look at it in the microscope where you can study the deformation holistically. So you can look at the entire deformation region as well as the micro and nanoscale details of the deformation. So the material system we picked up to study is a piezoelectric semicrystalline polymer called PVD-FTRFA. So this material is a rubbery material in room temperature. And what we did was we did two types of processing. One is we reduced the thickness of the material. And as you reduce the thickness of the material down to nanoscale, you see the crystallinity and the crystal size of the material goes down because of the geometric confinement effect. In addition, we also did thermal annealing above the Curie temperature, which brings back these beta phases that provides the piezoelectricity as well, and it tends to increase the crystallinity, as you can see when you do the thermal annealing. And if you take this material and shoot with microprojectiles at high velocity, you see about 1 kilometer per second impacts, and the dotted line shows the projectile diameter. And then, as you can see, from the anneal film, as you go down to thin film, you have decreasing crystallinity. And as you can see, the strain is much more localized here, and the deformation gets more and more delocalized as you go for thinner film. And as you reduce the velocity of the impact, you can see that the material in the anneal film, anneal material shows more of a brittle deformation. If you zoom in and see that, you can see that there are fibrillated crazes formed over here, which is characteristic of brittle deformation. But as you as you confine the geometry and go to nanoscale, that causes more and more elastic stretching and very large deformation delocalization. So if you look at the specific penetration energy, you can immediately see from an anneal film, from a thicker film to the thin film, you do see very high increase in the energy absorption, specific energy absorption. And if you compare to the crystallinity, if you increase the crystallinity, regardless of the thickness, it reduces the specific penetration energy. So why did this happen? As I said, it is the geometric confinement. As you confine the thickness of the material, you see that the crystalline domains will have hard time forming, so you have reduced crystallinity. Also, these crystalline domains will align more laterally in the transverse direction. In addition to that, the polymer chain lengths are now comparable to the thickness of the material, so the entanglement morphology in the amorphous region also will change in the material. So if you shoot this is what happens. So in a thicker film, it shows more of a brittle behavior, while the thinner film stretches, undergoes a large tensile deformation, and that leads to better energy dissipation. So what happens is, as you're stretching the film biaxially by the projectile, we would get these crystalline domains fragment, and as well as these polymer chains will get stretched and flow into the deformation region, while causing more mutual sliding between the polymer that can also engage piezoelectric effects. All these together have led to this increased specific penetration energy. If we compare this to other material, you can see that the graphene that was the best material is right here, the two squares, and then this thinner films dissipates very high energy compared to all of the material systems that have been studied before, both bulk as well as nanoscale material. So if you want to stop a 1 kilometer per second microprojectile, you would need about 10 layers of this thicker film versus about 19 layers of thinner films to stop the projectile. So you can think of sequentially placing them to create an ambient armor, at a standoff distance from the system you want to protect. And this system would allow you to reduce the weight by about 70% to achieve this very high specific penetration energy. So what you have seen is you have a very high specific penetration energy due to this polymer chain morphology changes as well as the crystallinity changes, and it engages a lot of viscoelasticity and viscoplastic deformation as well as dipole interactions in the piezoelectric material. So with this understanding, we want to go and study more complex systems like this nanofiber mats, both in polymers as well as these carbon nanotube type of systems. And we want to study the competition between the intrinsic as well as the extrinsic mesoscale interaction effects in this material system. So this is an ongoing study. So the second topic I want to discuss is, instead of using this as a destructive technique that you have seen, we use it for creation, okay? So what this creation is now, instead of launching a rigid projectile towards a target that you want to study, here you're launching a deformable projectile against a rigid target. So the projectile deforms against the target. So you will create a structure within the projectile that we are interested in studying. Again, we use the exact same setup at the Wisconsin to do these studies. This is something we have done to study a system called gradient nanograin metals. What these are is that, nanograins have shown to increase the strength of metals, but they reduce the ductility dramatically. So it can cause catastrophic failure of material. So mixing the grains didn't improve the properties beneficially, but instead, if you can create a spatial gradient in grain size, going from nanograins to larger grains, it can engage something called gradient plasticity that is due to the grain sizes associated with the hole pitch relation, where the strain will localize differently in different grains. So this leads to a progressive yielding situation where you can improve both strength and the toughness of metals. To study this, we have taken a single crystal microcube of silver that was fabricated by Sujin Jeon, who is a faculty right now in Korea. So these are single crystals that are defect-free and perfect cubic shape, as you can see. So this gives us a well-posed system to study this problem. So if you cut and look at it, it's one single grain. And if you take diffraction pattern, you can see that it is a face-centered cubic material. So it shows a very nice cubic diffraction in the material. So if you take this cube and compress it slowly, what you would see is, as you can see, this is a nano indenter that is compressing this material. It will compress and suddenly undergo an abrupt strain burst. What happens is, this doesn't have dislocations initially, so you have to spontaneously nucleate dislocation to cause this massive strain burst in the system. So what would happen if you take these cubes and launch it against a substrate at very high velocities? So a velocity of 400 meters per second correspond to a kinetic energy of the projectile, approximately 2.3 nanojoules. One thing I want you to pay attention to is that this 2.3 nanojoule is much, much lower than the melting energy of silver. So anything I will show is a solid state process. You don't see melting. And the strain rates are very high, all the way up to 10 to the power 8 second minus 1. So the very high strain rate deformation. So if you take this cube and impact, this is a face impact and an edge impact and corner impact of the cube. These are the side views, tilted side views, all taken in scanning electron microscope. You can see that very severe plastic deformation at the bottom impacted region, and the top region retains the initial structure. And also you can see characteristic slips coming from these that are characteristic of these intrinsic crystal symmetries. This face-centered cubic material has 100, 110, and 111 symmetric direction. They correspond to this corner, edge, and face impact direction. So they create this slip system that exits the crystal, as you can see. So if you take this cube and cut it and look at it in the transmission electron microscope, we can study the nanostructural deformation that happened inside. So what we think that caused this deformation over here is that if you do a simple normal shock calculation, you will see that the pressure in the material goes all the way up to 10 gigapascal. The yield strength of silver is only 60 megapascal. So this is a huge stress. So that will take the material into hydrodynamic stress state in the bottom region. That will shape the materials over here, the deformation of the material. While the stress field will interact with the free surfaces to cause attenuation, so the top region deforms mostly by ordinary crystal plasticity. So if you look in the TEM, you do see these characteristics of two stress cascades at play. So you see more single crystalline region at the top, and it progressively becomes nanocrystalline at the bottom, as shown by the selective area diffraction. You can go into more details of this diffraction, and when you look at the diffraction pattern, it turns out they don't show this cubic symmetry anymore. Instead, so the face-centered cubic silver supposed to have this 111 plane in an ABC stacking order that repeats, which is called the 3 cubic stacking, 3C. But it goes into a hexagonally closed back system. So there have been a martensitic phase transformation that happened in silver that taken this face-centered cubic system into a hexagonally closed back system that has an A, B, C, B stacking order that repeats itself. To confirm further, we studied hundreds of selective area diffraction images and compared again the standard diffractions, and it indeed confirms that there had been a martensitic phase transformation. Of course, it is not us the first people to discover that silver has HCP system. It has been discovered in Russia in 1980s or 79 in Siberian gold silver mines, where they noticed this hexagonal silver. And as well as in India, people have observed this forming due to high pressure magnetron spattering. This has also later been seen in nanowires that are occurring. All these are slow kinetic processes that cause this phase transformation, whereas ours is the first evidence of a martensitic phase transformation due to a physical process of impact. Whereas if you look at the edge impact of the cube, they do not show this phase transformation, and they also tend to stay more or less single crystalline throughout the material system. To understand this further, we collaborated with Mauricio Ponga from British Columbia to do molecular dynamic simulation, which showed us the stacking fold that have been created emerge here, and then they form these large hexagonal close-packed regimes. Whereas this does not happen in the 110 direction of impact. If you look at the molecular dynamic simulation, they also show that one of the system that when you impact on the phase, they cause this gradient nanograin structure, whereas the corner impact or the edge impact does not cause the favorable gradient nanograin impact of the system. So the key findings are that we do see the intrinsic and extrinsic particle shape as well as the crystal symmetries playing a role in the deformation, as well as we do see the role of two hydrodynamic and crystallographic stress states playing a role, okay? So what we want to do with this is currently, with the aim of creating ultra strong and tough material for extreme application, we study the structure property relation in the material. We characterize the structure through the transmission electron backscattering and then connect them to the nano indentation properties of the material. And also this can be looked at in a material processing fashion, where you can launch these microparticles to harden a surface or else create coating. So any understanding we develop in single particle impact in our laboratory system will allow us to improve this material processing system as well. With this, let me acknowledge my lab members, particularly Dr. Jiju Kai, who is a postdoctoral researcher in our lab, and Claire Griesbach, who have done most of the work that I have presented today. And let me also thank my collaborators, Mauricio Ponga from British Columbia, Sadek Yazdi, who have done TEM microscopy, who is at Colorado Boulder, Sujin Jion, who synthesized the silver cubes from Korea, and Edwin Thomas from Texas A&M. He was at Rice and just moved there. He was my postdoctoral advisor, and we continue to collaborate in a fruitful collaboration. So this was a fine evening in Madison long before the COVID hit us. So let's hope that we get back to this again. Over to you, and I would be happy to take any questions. I think we'll do that at the end of the next presentation. Thank you.
Can you on
You have to wait. I like to give the stage to Julianna. She got her bachelor's from University of Cincinnati, master's and PhD from University of Michigan. So Julianna, you right now.
Juliana,
All right, can you hear me?
Yes, we can hear you now.
Okay, fantastic. Well, thank you so much for having me. I'm really excited for this opportunity to share my research with all of you. And I'm excited to tell you about a few of these new projects that we've been working on. Today, I'm going to talk to you about materials mechanics and manufacturing of multifunctional yarns and textiles. So multifunctional yarns and textile enable applications. And so we're interested in a whole host of applications A lot of people just think about wearable applications when they think about yarns and fabrics in general, but we're interested in transportation, so creating programmable surfaces to control flow over a surface. Medical devices, there's already been a lot of work on creating endografts and surgical sutures for implantable medical devices. We're also in wearables, moving into active compression garments for both medical spaces and aerospace. And similar to last year, we're interested in defense applications and things like impact absorbing helmets. So that can be used for defense or for recreational use. And there's a lot of work in this area enabling soft robotics for a whole host of applications. And there's a tremendous potential for enabling energy harvesting through different effects within the textile structure. We have some common needs within these structures to create tailored and improved performances, greater wearability. So some of these things, we're getting more and more wearables on the market, but they're often actuators or systems just attached onto existing systems. So the more we can create integrated yarns and fabrics, the more highly adopted these products will be. We want to increase wear resistance because that's important for use, and improve corrosion resistance. And so in my lab, we look at all of these factors. And my lab is the Design of Active Materials and Structures lab. And our goal is to combine innovative design processes and advanced manufacturing techniques with material and structural modeling to lay the scientific foundation necessary for the rigorous design of multifunctional fabrics. And so we have several different projects that we're working on now, and I'm only going to highlight a few of them today. So I'm going to talk about understanding the multiscale mechanics of these structures. So we're going to hear a little bit more about multiscale structures in this talk. And we're going to move on in those key takeaways and findings from these studies and how we can use them to implement and create new wearable technologies. And then we're looking towards new materials and manufacturing methods to move into textiles that look more realistic. And so we're looking at the manufacturing of microfibers, yarns, and textiles that have design performance. And finally, if I have time, I'm going to share two other applications where we're really, because of the multiscale mechanics we're developing and the design techniques, we're going to enabling some new applications like non-pneumatic tires and some innovative costumes. So I'm excited to share all this work with you today. So first, but before we can dive in, we really need to understand we're mainly going to be working with the shape memory alloy system, or we're only going to be working with the shape memory alloy system today. We work with some other materials within our lab, but this is the only one I'm going to talk about today. And so in order to understand how these systems work, we have to understand how the material itself works. And so many of you are probably familiar with shape memory alloys. And the most common effect is the superelastic effect. And that's what's been implemented in countless implantable medical devices. Where you are above a transition temperature and you exhibit this constant stress plateau. So you are linear elastic for a portion of time under loading, and then you undergo this constant stress plateau, and then you can recover all that deformations upon unloading. And so these materials, you can see, witness up to 8% strain out of them, recoverable strain. And this is all at their high temperature above the austenite finish temperature. Another common application that's been implemented, or effect that's been used frequently is the shape memory effect. And so that's when you're actually changing the temperature. So instead of just dealing in stress strain space, now you're dealing stress strain and temperature. And so you're going from a cold, flexible, martensitic state, and then as you heat it up, you're going to recover those deformations in the wire, and you can do mechanical work during this process. And there are a couple other factors and effects of shape memory alloys that we'll kind of be on the edge of using throughout this talk. We have recovery stress generation, and so that is when we take a material and we stretch it to a certain length and we hold it at that length, and then we change its temperature and we can generate stress within the material. We can change its stiffness. And we can also exploit the two-way shape memory effect, where we have two memorized shapes that we're moving between through thermal transition. So we're going to focus on the shape memory effect for most of the talk, with one application that towards the end that involves superelasticity. So the other important component of my work is the architecture. And so there's really 6 common architectures that are frequently used, textile architectures. And so you see 2 of them on the screen right now. Knitted structures are made with a single fiber that with interlacing adjacent loops. You have a lot of bending strains induced during the manufacturing process, and these are known to be very stretchy. And this is, if you're wearing a sweater today, it's probably going to be knitted. Whereas woven structures are much more stiff and rigid. You have multiple fibers and parallel toes or triaxial toes. And so you get a very rigid statement. And I really like how it was shown in this article from the Jaeger group, comparing the performance of a single fiber. You have regardless of what your base material you're using, you have some initial fiber performance. And as you stretch on this material, you'll see whatever performance is given. Once you integrate it into woven structures, you have these slight bends that you're inducing. And as you pull on it, it's a little stretchier than the base material itself. And as you integrate it into a knitted structure, you have large bending deformation. So you get a much more flexible structure, and you get this J-shaped curve. And this J-shaped curve is interesting for a lot of reasons. We like it because it's really close to human tissue. And so you're getting a mechanical response that's getting closer and closer to what your human body exhibits. So it's easier to create applications that will match with your body's performance. So combining these two things together, when we have knits and weaves, we have this hierarchy of performance. At the first level, we have these bent loops. And when we make it out of shape memory alloy wire, we have this initial structure. We're going to heat it up. We get large contractions over a surface. We go up to the next level, and we can tailor our pattern. So we can have knit and purl loops in certain patterns. This happens to be a rib pattern of varied columns. It's the edge of all your sweaters. And when you heat it up, it goes from a flat surface into this corrugated wavy surface. So you can imagine using this for some type of flow control over a surface. The next level is creating heterogeneous patterns across the surface. And so we have grid patterns. This is half rib and half stockinette. So the rib portion accordions in one direction, and then sequentially the stockinette comes over and folds. So we get sequential actuation with spatially distributed motions in different areas. And then we can create structures. We can enhance our forces or displacements by going from a 2D element into a 3D structure. And so this is a tube that acts as a deployable boom to produce 400% actuation strain under more than 5 times its weight. And so we have a lot of potential at each of these levels to add in, to tune behavior for different applications. And so this was really based off of one of the papers I did my grad work, and we're going to be moving off in a whole bunch of different directions to better understand this phenomena and implement it in different systems. So first, I want to talk about multiscale mechanics of knitted shape memory alloy actuators. This is work primarily done by my graduate student who graduated this summer, Kevin Eschen. He got his PhD this summer. And then I'm just going to hint at one thing we did with Javier Garcia Barracanal at UMN CareFax Center. And because there's so much work here, and I'm only going to show you the things necessary for you to understand throughout the rest of the presentation. I'd be happy to discuss any of these topics with you, though. So why do we even care about the multi-scale mechanics of these structures? It's because at each scale, we have effects that have determined the whole performance of the system. So the microscale, we don't know how our microscale behavior affects our design performance. And at the mesoscale, we have these different loop structures and geometries that we are not sure of how they impact the performance. And then we have a macro scale. And so how do we combine all these things together to create usable design tools? So we're going to start up here at the macro scale because it is the easiest to conceptualize. Knitted structures, like I said, they're interlacing loops of adjacent unit cells, and they're pulled through one another on a knitting machine that you see on your right. And so depending on how far apart those needles are spaced and how far they pull them back, you get different loop sizes. And this is a simple garter knit. And so it's going to provide in-plane contraction like you saw in the previous example. And so we're getting about 50% in-plane contraction distributed over a surface. And then the performance, how much it actually contracts, how much weight it pulls, is all a function of the geometry. So you have a wire diameter, you have loop sizes, you have number of loops in the horse-wise or whale-wise direction. And so we can tune all those parameters to get a performance for an application. And so to characterize these, we conduct constant force actuation tests where we apply a weight to a sample in a cold state. We heat it up to see where it contracts to, and then we cool it back down. And we do that a couple times. We increase the applied load and cycle through. So we can get 2 sets of curves, one on the left here, where we have a martensitic curve and an austenitic curve. And the one on the right here is just the difference of the two with the austenite as its, or with the martensite as its reference state. So we call the one on the right actuation contraction. So that's the relative contraction at any given load that this textile can produce. And these are very small swatches. So you're seeing a peak force at 1 Newton for this given geometry. But we've done this for a lot of different samples, and we've been able to characterize and create macroscale relationships. So we've identified this knit index parameter. It's the ratio of the area over the diameter of the wire squared, and that really governs the maximum actuation contraction we can get from a structure. And we found this very useful for designing applications. And you can see the different knit index. When you have a low number, it's a more densely knitted structure. The higher the number, more open and porous that structure is. And so the more open and porous it is, the more actuation contraction you're going to get from it. And so we've gone from that macroscale relationship, and we wanted to understand the microscale mechanics. And so we have a whole paper on this X-ray diffraction experiment that we did. But what we were able to do is to zoom in on a single knitted loop. And then we had a very small point of view of the X-ray. And so we were able to look along the length of the wire at 5 different locations, and then across the diameter of the wire at several locations. And then we were able to determine the austenitic phase fraction at each of those given points. So through this test, we determined that this is really a bending dominated structure. We've also developed a Mesoscale modeling approach. And so at the top, you see the experiments with very qualitative data. There's a lot of quantitative data in the paper, but you can see that as we go through, we have a larger austenitic martensitic phase fraction up at the top because it has a large bending radius. And then here at the inflection point at the base of the loop of this repeating structure, we have the lowest martensitic phase fraction. And so we get this distributed portion. And what was interesting is this purple dot up here was unexpected to us because we thought because of the bending strains, how they're applied, that we'd be decreasing all the way throughout the structure. However, the compression within the structure between adjacent loops increased our stress at our contact points. And this was great. We developed a model based on finite element methods that captures both the nonlinear geometry and deformations and the nonlinear material. And we see the exact same thing through this model. So now not only are we able to predict the macroscale behavior, we're able to know the local stresses within the material. And this is really important because when you're working with shape memory alloys, you want to minimize the strains, because if you go to strains that are above 4 to 8%, so you're going to get decreased repetitive performance. So now we understand what our strain distribution through our material, and we can tune our architecture to achieve the performance we need. And so now we're going to move on to how we're using this information. So we're designing self-fitting and compression wearables. And so really this is Rachel Granberry's work, and some of the projects have been done with Kevin Ashton. Rachel is a apparel design student, co-advised by me and Professor Brad Holshoe in the apparel design department. So what is a self-fitting garment? New wearables require accurate fit. So you have exoskeletons where you have multiple actuators within a system. However, if your connection point on the body drifts over time, you're going to have a reduced mechanical performance. Likewise, you have all these wearable sensing garments that are hitting the market. And if your sensor isn't properly placed, you're not going to be able to reliably use the data that's being collected. You also have VR and haptics systems. So being able to convey information back to the wearer is really a big emerging area of interest. So we're looking at how do we use these materials to create self-fitting garments. So the concept is we'll start with something like a pair of pants that's cold, flexible in the martensitic condition. And so it's easy to put on. So as you put it on, your toes poke into your legs and the garment kind of stretches out a little bit. And we end up here with a little bit of stress in that garment as we're putting it on. And once we get it fully up, it relaxes and it recovers a little bit of that deformation. And then ideally, the material is tuned to operate right around your body temperature. And so at this point, it starts warming up and it contracts and it gets smaller and tighter on the body until it reaches this point 4. And upon further contraction, it's operating in a force blocking mode. And we've got it to the point where it's applying a pressure. And we want to limit that pressure for a self-fitting garment to that traditionally applied by a slock, which would be about 15 millimeters of mercury. And so in order to design one of these prototypes, we conducted an anthropometric analysis. to guide the design. And we used Kevin's leg as an example to create this garment. And so we created, on the left, you see the body dimensions in red. And so that is what we want it to be when it's in the hot state, because we want this garment to be perfectly fit the body. And in the blue, we have the size necessary to properly don the garment, so pull it over your ankle. And on the right, you see the pattern making approach and the different knit indices that you need throughout the garment to achieve the percent contraction. And so we actually created this garment. On the left, you can see the image, the stills of it. And on the right, it's made with Dynaloy Flexanol 70-degree C wire. And so it's being heated with 2 heat guns. And you can see as it's being heated, it shrinks and perfectly conforms to this plaster cast leg. And so we were able to quantitatively assess this contraction through image tracking using our correlated solutions Vic 3D system. And you can see in the gray is the bare leg, red represents the contracted form of the garment, and blue is the don form, or the stretchy, flexible, cold form. And we can see the red and the black line match very well, so we're getting very consistent performance and contraction over the course of the body on the macro scale. However, when we look at distribution around the form, we're seeing that we have some issues with topography. And so the human topography greatly affects the performance. So if you have a concave region, we were seeing that you would just bridge your concave portions and not actually fit the body in those regions. And so we were able to use those structures I mentioned earlier, where we're getting these different bending motions in different directions, to create a functionally graded garment that would perfectly conform to the geometry of the leg. And so through that process, we went from low contraction numbers up to very high contraction of having 86% contact around the surface of the leg. And so, but what we really want to do is we want to be able to operate these on the human body. And using that Dynaloy material that requires a heat gun is not feasible to put on the human body. So we work with Fort Wayne Metals to get a material that worked for us. And so this material, instead of having a very high transformation austenite finish temperature of 76 degrees that we saw on the wire, the material, the NiTi number 4 we got from Fort Wayne Metals had an austenite transformation temperature of 36.5. And so that is within safe realm to operate on the body, because you can go up to maybe 45 degrees without causing burns. And so we're really excited to have access to this material so that we can demonstrate this on body. We only have a small amount, and so we did a wrist garment, a self-fitting wrist sleeve, and used the topography of the wrist to have a custom design pattern. And when we pulled it over, it followed a very similar qualitative performance, where initially it's flexible, you stretch it on over the garment over your wrist where it's larger, and once over your hand where it's larger, once it's on the wrist, it relaxes and the body heats it up and it starts to apply some pressure. So we're really excited for this, but what's next? We also want to go from just creating those low levels of compression of 15 millimeter mercuries to medical grade compression. And so there are numerous medical conditions that rely on on-body compression: orthostatic intolerance, hypertension, DVT. So there are a lot of different medical conditions that would benefit from enhanced compression garments and enhanced compliance of wearing compression garments. But at the top right, you see a proposed operation where we'd have a garment with strategically placed active panels. You put it on in the cold martensitic state, and you might have some zippers to facilitate this. As it heats up, it will start to tighten and apply pressure to the body. And then at the end of the day, and throughout the whole course of the day, you won't need any power to provide that compression. And at the end of the day, you can unzip it and take your garment off. And then you see below our first on-body prototype that we shared with the ISIS conference this summer. So it's great, but you saw in that last image, the knitted area is not what we think of as a fabric. It was very much a textile, an open porous textile. And so we're looking to the next generation of these and how do we make these more wearable? And one way is to look at how we manufacture NiTi spun microfilament yarns. And so this is done in collaboration with a group from Fort Wayne Metals who are producing this material. So yarns produce torsional and axial actuations. There's been a lot of work on this recently, using different material systems, shape memory alloys, shape memory polymers, carbon nanotubes. and different yarn architectures. And they all, typically they either use a thermal expansion or some type of swelling effect in order to provide linear torsional actuation. And so we're looking at how do we enable this with shape memory alloys, because right now, if you look at what's commercially available, they're pretty large diameter wires, and so it's hard to make a yarn out of diameters on that scale without causing permanent deformation. And so, and we really want to understand this coupling between the material that we're using, the geometry of the yarn, and the manufacturing parameters. And it's a really well-established relationship that our manufacturing twist, our density, and our packing length all rely on these manufacturing parameters that we see in our system. So we're using a traditional ring spinning technique to create these, where we have a bunch of parallel fibers that come into our system. They're all twisted together, and depending on our delivery speed and our spindle speed, we get different amounts of twist. And also, because we're applying twist, we have different fibers in different regions. So we have the center fiber that's straight, that's acting as just a linear actuator, and then we have these torsional or helically twisted fibers around the outer edge. So we have a really complex interior stress profile, and we're trying to understand that relationship of where we are in the structure, how we apply twist to get a desired macroscopic performance. So how are we making these? We're getting these bundles of filaments from Fort Wayne Metals. We have gotten things between 5 and 10 microns, and bundles between 4 and 1,000 different bundles, and they etch away the iron matrix that they draw them in, and then we bring them in and we do some thermal processing within the lab in order to stabilize our transition temperatures and twist set or stress relieve the yarns. So some preliminary results. We've noticed that we see these strong trends that depend on twist. So if we increase our yarn stiffness, we increase our, or if we increase our yarn twist, we increase the stiffness, or we decrease the stiffness of the yarn. And the same thing with strength. So as we increase the twist on the yarn, we're getting less and less strength. However, there is an optimal point. With more twists, we're also seeing this varied recruitment into the structure. And we're seeing these interesting regions where we're transferring over a larger range. So when we're going from austenite to stress-induced martensite, instead of having a very sharp transition that we see in parallel fibers, we're seeing this gradual transition that could actually be useful for some applications. And we're seeing this reduced hysteresis band. Additionally, we can tune the architecture to go from a single ply to 2-ply, and that's going to scale our forces and just give us a slightly reduce our structural strain. And we can decide when we heat treat these. If we heat treat the yarn and then spin it, we removed all those residual stresses initially, but then we introduce them in the spinning process, and we have a very active yarn that wants to furl. And so we can get it, and when we want to use these as an actuators, they provide a lot of twisting motion. If we spin it and then heat treat it, we're removing those stresses, and we create a torque balanced structure that's really easy to work with traditional manufacturing equipment. You can see as this one is held slack, it just drops, and there's no pigtailing. And so through this heat treatment process is another knob that we can tune to create the mechanical performance that we want. So we'll go from the yarn into a structure, and this is 100% nitinol, all these fine nitinol wires in the black, and this is using the shape memory effect. So it's a 3-ply knitted garter structure, and as we heat it up, we see we're recovering those deformations just like we saw in the monofilament knitted structures. And we also see the shape memory effect. So on the left is below the austenite finish temperature. It's not very active. It has some structural response where it wants to recover, but when we heat it above the austenite finish temperature and remove a weight, it's very active and wants to recover its initial shape. And so we see a lot of potential using these manufacturing methods to create garments that people would actually want to wear. And because it's nitinol, it can potentially be useful for implantable medical devices. So just 2 last really quick applications, emerging applications. So these are both applications that Henry Kuhn, who's a graduate student in my lab, has worked on. One of them is done with Santo Padula from NASA Glenn Research Center, and the other is done in collaboration with Denny O'Malley. So the first one is rover tires. There's a big issue with rubber tires failing due to their non-compliance. NASA Glenn has a spring tire that's made out of nitinol that they're investigating right now. And we think knitted structures would provide a great next generation application for these materials. And so we have a non-pneumatic tire. Has some very simple component, has a wheeled hub that's not optimized, a rim. It includes superelastic radial elements to carry the weight of the vehicle, and a superelastic knitted tire tread. And so here's what it looks like. And so it's a very densely knitted structure where we're leveraging shape setting of the material and the pattern to create better texture. And you can see it going over a very large object. It envelops this sharp, awkward shaped object. It would not pop the tire. This tire can support 50 pounds as designed. And you see as it rolls off, because of how it's designed, it pops back out and it's completely reusable. So it's very useful for rough terrain. And the last one I want to share with you is engaging communities with STEM. And so we're talking about all these different techniques and approaches to create multifunctional yarns and textiles. And it seems really abstract, some of the applications, but it's great to reach out to the public and get them engaged. And so we were able to do this collaboration with the Department of Theater, Arts, and Dance recently. And we created a linkage-based frame and used shape memory alloy coils to create a robotic angel rings for this play. And they were actually worn on stage multiple nights. And she's wearing a leather jacket that has a battery pack in the back, and she has a button in her sleeve. And whenever she wanted to in the play, she just pressed the button on her wrist and the wings came up. And they were very robust. She climbed scaffolding, and it was really fun being in the crowd watching it, because there were some young kids in front that were just amazed by the wings, and they were trying to talk, because we had a small blurb in the program, and they were learning about the material. So while it's not the most challenging application, there's just so much potential to engage new students with these types of applications. So I want to acknowledge all my collaborators and my students. My students work really hard. And we've had a lot of graduate students work on these projects and undergrads. And again, these are, like the speaker before, these are all older pictures. Unfortunately, several of these students are not shown because we haven't had a get together recently. But yes, thank you. I'm happy to take questions now.
You did excellent in terms of being on time. So let's see, there are some questions. I'm going to look at question is about how do you model, I think this is to Julianna, the point of contact between two fibers. You understood the question, right? How do you model the point of contact between two fibers?
We are using a sliding contact model to capture. And so we are we're looking at interference and moving nodes, and we have a very traditional and rudimentary approach to doing friction between two loops. And we're only modeling friction between two contact points right now for the monofilament structures. For the microfilament structures, we have a model that we've developed that looks and models contact as hydrostatic compression within the yarn itself.
Okay, very good. Let's see, any other questions? I'm trying to see.
May I ask? This is Arun Srinivasa from Texas A&M. Very nice talk. Thank you very much, Julianna. I had a quick question for you. For the shape memory effect, one of the biggest issues is durability. That is, how many cycles can you do, especially because of the point that JN made about rubbing, because it generates heat and you will destroy the connection, especially with shape memory. I think with super elasticity, I think you can do very well. I think that's less of an issue. But shape memory, I'm concerned about the fact that it may run for a few for a short time, you can be able to do cycle back and forth. And after that, we saw that it would quickly die, especially in places where there's heavy curvature.
That is definitely an issue. We are seeing consistent performance. We see degraded performance over the first 7 to 12 cycles, depending on our loading and our structure, and we get consistent performance up to hundreds of cycles.
Yeah. Okay.
But we haven't tested beyond
Yeah.
beyond
So
that.
that's. I mean, my student Ashwin Rao and I, we ran a lot of experiments on springs because it's nice coil, so you can get nice curvature, and we found that 1,000 cycles after that, you really get into trouble.
Yeah, we have not got up to that high cycle fatigue yet, or not, that's not even high cycle fatigue. There are definitely issues. There are, the microfibers are not available in coated form, but we can do some coating. And have done a little bit of coating on individual fibers within the monofilament structure, and that definitely helps with those contact points.
Yes, thank you. Thanks.
And we're really excited for all of the modeling tools that we've developed recently, because we can minimize those local stresses, which makes a huge effect in creating repeatable performance.
Yes, thank you.
So, Julianna, did to embed SMA fibers in polymeric materials and
we
use
have
for
done
application?
Yeah. So we've created some smooth surfaces, creating really rudimentary composites where we have the monofilament SMAs in the rib architecture, for example, just using dragon skin, like a really quick mock-up in the lab. And so we can get that corrugated surface in a polymer structure. We get slightly degraded heights from our structure compared to just the textile itself, and slightly lower forces because we're fighting against that structure. What we found is when we put it in a composite with the monofilaments, at least, it creates gaps. So as the wire is heated, it actually burns through, and we have pockets where it's operating in those pockets. So we are not, it is fully delaminated within the structure, but because of how porous that structure is and how it's distributed, it just operates in that little delaminated region, and we can get that smooth surface on top. So we've also been able to create smooth surfaces by sandwiching it between two passive fibers and sewing it in place. And so because they're so very open structures, so we can put a like ripstop nylon on top and the below and sew it in place to create a smooth surface.
Okay, very good. Thank you, Julianna. Question to Thevamaran. Using your first name, which happens to be also last name, I understand. Right. But anyway, did you have done any continuum modeling of these materials? When I say continuum, means you go to the micro or nano level, but you want to get some features by doing some modeling. So you may want, so did you do any?
Right. So for the gradient nanograin structure, right? So that is something right now we are doing, not for the impact part, but after forming the structure, we can get the gradient nanograin structure characterized. So then what we are trying to do is the crystal plasticity finite element model is something we are trying to develop so that we can associate the hole pitch effect with the grain size and try to study the collective effect in the material system. So that's something Clea is currently working on. For the problem in the polymer, it is challenging to do continuum level modeling because the material is changing the moment you start to so regarding the scaling up and then trying to do continuum modeling, there are two problems, right? One thing is the scaling up with the microballistic to macroballistic system, what type of a scaling exists with the projectile size. That scaling is fairly scalable to our understanding as long as the material is the same. But what we are seeing is that the moment you try to go into nanoscale and get the material confined to a critical dimension, the entire morphology and the properties and everything change. So we don't have a clear understanding of every single property. Say, for example, PVDF material typically has stiffness anywhere from 2 megapascal to about a few gigapascal, couple of gigapascal, depending on the crystallinity in the bulk form. But the moment you make a nanofiber with PVDF TRFE, that is about 80 gigapascal. Right, so these are measured values. So there is a lot of uncertainty about this nanoscale phenomena that happens. So if we can understand that, then certainly we can go for more continuum level modeling. That's something we are trying to.
So a follow-up question is there any way to bring this changing properties into your constitutive model with some way to bring the change in material properties? And second, if you go to continuum model, maybe there is a way to bring the characteristic material length scale into the modeling at continuum level, because we cannot use finite elements cannot be done. You need trillions of degrees of freedom.
Right.
Okay, not just billions.
Right. Absolutely.
So it's not possible. So you have to, since you are going to continuum level anyway, you have to make some kind of modeling assumptions.
Right.
But bring the lower length scale information to the continuum length scale. So is there some thinking going along those?
Right. So this is again another problem that I'm talking to one of our colleagues in the department, Dr. Kurt Bronkhorst. So he studies these type of metallic systems in an impact high strain rate deformations. So we are trying to develop such things, but then the models have to be developed such that we capture both the phase transformation and the grain refinements associated with that. So that is something we have to do in a consistent fashion. That's something we have to do. But for the polymers, we haven't tried anything so far in the continuum approaches yet. So that's right. As you suggested, we need to incorporate this material characteristic length scale into the problem to do that.
So there are a couple of questions from the audience. How are the thin films in your work are being manufactured?
Right. So the thin films, we do the standard spin coating method. So you can vary the spin coater speed in order to cast the film in different thicknesses. So we went down up to about 73 nanometers, where the particular polymer we took, the polymer chain lengths are around like 43 nanometers. If you assume it to be amorphous and calculate that. So we are getting down to a scale where there will be morphology changes induced due to that. Then the other type of processing, as I mentioned, we do is to do the annealing post fabrication, so that you can change the crystallinity of the material while keeping the thickness more or less the same. So that's how we fabricate. So this is basically scalable fabrication method. If you want, you can do it in a large scale. Only question is now, how do you make the armor? So that's what as I suggested in the last slide, you can think of making multiple thin films and putting them together and then create an ambient armor which will be sequentially penetrated. In aeronautics conduct, it may be thought of like a Whipple shield that you would like to put at a standoff distance. Right.
Another question for you is, can you orient the particle on the fly on specific orientations? For instance, using electromagnetic fields.
Right. So we haven't went into that detail of like exactly orienting in a particular direction. So right now what we do is we shoot the particles and they orient themselves depending on the aerodynamic conditions we have. So it is certain probability of corner impact versus edge impact versus face impact you would get. And the face impact is the most hardest to get. So if you shoot like 100 times, you would end up with like 10 face and then like say 20 or 30 edge and then more corners you would end up with, right? So we don't control that, but certainly that could be a possibility with some other fields present in the system. Right now we are doing in the ambient conditions.
Yeah, there is a possibility of interference also because of the speed. So you have to be
absolutely.
careful.
So if your material, right. If your material is sensitive to that, then yes, you're going to have some material behavior change due to this. Yes.
Right. So but I'm thrilled and excited of you, our mechanics future. I would say that very, very interesting. And what I observed in the presentations is the not only very, very basic research components, but also very useful realistic modeling applications. So, and both Juliana and you have done great deal, and I probably have more appreciation for Juliana's work because of my own background, less material science, more mechanics. So, but I'm very, very complimentary of your works, and I really wish success in coming years. So stay focused and always think about how can I make impact on the. I mean, these are big words, but I mean in your own way. It doesn't have to be Einstein level kind of contribution, but in any small way, you can advance the with your understanding of the various aspects of what you're doing and sharing with colleagues through your publications, of course. So if there are no other questions, is Devesh, are you going to say something?
So there are a couple of questions still, Jen. So there's one question for Juliana. It's about your opinion on Perseverance rover wheel design versus Curiosity rover, and how is your wire mesh design better than what they had before?
Okay, Perseverance rover's wheel design versus Curiosity rovers, and how is your wire mesh design better? Okay, I mean, I'm not sure exactly.
Yeah.
But can you read this? Can you read the
Yes.
chart? Okay,
Yes, I can.
please. That's much better.
Yeah, the tire project is very preliminary. We made one version just to get across our idea because people were thinking fabrics like you wear. So we did a back of the envelope calculation to create these fetch rover metrics. And so I think we have a lot of potential with the knitted structure compared to the current design. The knitted structure gives us that compliance, added compliance that's missing. We have we're leveraging the superelastic effect in many different ways. So we are able to support loads through those radial elements, and then we can accommodate deformations through that knitted structure. We have a lot of potential with our mesh because we can control so many of those parameters. What I showed on the tire is just a 2D knitted structure, but there are a lot of 3D knitted structures out there that provide a gap. And that's going to be really important for flotation on the surface. And so you get the right amount of sinkage. And so our idea is eventually to create a tire with some through thickness. And we're going to be controlling our porosity of that tire. And so we can change the wire diameter and our loop size and to look at that soil mechanics. Basically, with this design, we have more knobs to tune than the current design. And we can also, when you think about sweaters, you think of all the sweaters you wear in the winter and you have all the different patterns, right? So those are different topologies, and those topologies could be used as browser elements within a tire. So we can use this knitted structure, the structure itself, while we're not actuating it, the structure is multifunctional. It's providing flotation, it's providing grip strength, it's for accommodating deformations. And so that's why we think there's a lot of potential with the knitted structure within the tire. And not just for rover applications. I mean, what we built was actually meant to go on a moped, but we have not done that yet. It only supports 50 pounds, so maybe the next gen.
Very good. So Wendy has any more announcements or anything?
No, I think we have done a really nice job. I do want to thank you again for moderating this session for us, Jan, and our speakers for giving fantastic presentations. I welcome everyone to join us again in the coming weeks and watch out for the announcements and the themes. We also have a website for the upcoming seminar talks, so you can track things on there as well. Devesh, any other things that we should comment on?
No, thank you, Wendy. I think we'll keep it session open till 5. So if you want to turn on your video and you want to interact with the speaker, it's free for you guys if until 5 o'clock. We'll
I
stop
agree.
recording, so it
Yeah,
could be
this is what we call cocktail hour. Okay, so have your own cocktail